Good day everyone. At this lecture we're diving into the world of hydrodynamics, starting with the basics of fluids. A fluid is a substance that flows, and there are two types of it, liquids and gases. Aerodynamics studies air and other gases in motion, while hydrodynamics studies liquids. Let's discuss some fundamental properties of fluids. First, density. Fluids, whether liquids or gases, are defined by their density, the mass per unit volume. This characteristic dictates how substances interact with and move through fluids. The concept of density is foundational in comprehending buoyancy, fluid behavior, and the classification of materials as either liquids or gases. Another crucial property of fluids is viscosity. Viscosity is the resistance of a fluid to deformation or flow. Whether it's the flow of oil in pipelines or movement of blood in our circulatory system, viscosity is a key parameter which defines the flow type. The force exerted by a fluid is encapsulated in the property of pressure. Understanding pressure is essential for grasping fluid dynamics. From hydraulic systems to atmospheric phenomena, pressure is a driving force that shapes the behavior of fluids in diverse contexts. As we move on into hydrodynamics, keep these fundamental properties in mind. They form the basis for comprehending the dynamics nature of fluids. In fluid dynamics, flow refers to the continuous motion of movement of a fluid. This movement involves the transportation of particles within the fluid and can occur in various directions and speeds. The study of fluid flow encompasses the examination of how fluids behave under different conditions, including the factors influencing their velocity, pressure, and patterns of motion. Flow can be categorized into different types based on the organization and predictability of the fluid particles' movement. Two primary classifications are laminar flow and turbulent flow. Laminar flow is characterized by smooth, orderly, and predictable movement of fluid particles. In this type of flow, particles follow parallel paths without significant disruption or mixing. Imagine a gentle stream or a slow-moving river. The calm and regular movement exemplifies laminar flow. Laminar flow is often associated with low fluid velocities and is prevalent in situations where a fluid encounters minimal obstacles. On the other side, we have turbulent flow, a dynamic and chaotic motion of fluid particles. In turbulent flow, the fluid undergoes irregular fluctuations, mixing, and eddying. Picture a rushing river, a waterfall, or a turbulent wake behind a moving boat. These scenarios exemplify the complex, unpredictable nature of turbulent flow. Turbulent flow is common at higher fluid velocities and is influenced by factors such as obstacles, changes in direction, or variations in viscosity. Understanding flow is crucial in fields such as physics, engineering, and meteorology, as it plays a fundamental role in the design of various systems, from pipelines and aircraft wings to weather prediction models. To predict the flow patterns in different fluid flow situations, the dimensionless parameter Reynolds number is used. It is named after Osborne Reynolds, the British engineer and physicist who first introduced the concept in the late 19th century. The formula for the Reynolds number is on the slide, where the length is a characteristic linear dimension of the flow, diameter of a pipe, for example. The Reynolds number is a critical parameter because it helps determine the flow regime of a fluid. It indicates whether the flow is laminar, turbulent, or in a transitional state between those two. For low Reynolds numbers, the flow tends to be laminar, with smooth and predictable fluid motion. This is common in situations where the fluid velocity is low and the viscous forces dominate. For intermediate Reynolds numbers, the flow can be in a transitional regime, exhibiting the characteristic of both laminar and turbulent flow. This transition is influenced by factors such as pipe roughness and disturbances in the flow. For higher Reynolds numbers, the flow tends to be turbulent, characterized by chaotic and irregular fluid motion. Turbulent flow is prevalent at higher velocities, where inertial forces dominate over viscous forces. The Reynolds number is widely used in various industries, including aerospace, automotive, and civil engineering. It is a critical tool for predicting and controlling fluid flow in applications such as pipe systems or aircraft design. Visualizing flow using streamlines, streaklines, or path lines makes it more intuitively understandable. A streamline is a line which smoothly connects velocity vectors at an instance in time. In other words, an image of the flow characterized by streamlines is like a snapshot of the flow at one moment in time. A streakline is a curved line formed by a string of fluid particles which have passed through a certain point. An example of a streakline is a trail of smoke from a chimney. A path line is a path which a fluid particles traces. One example of a path line is a path defined by a balloon floating in the air. For a flow which does not change with time, the streamline, streakline, and path line are the same line. A flow which does not change with time is called a steady-state flow. On the other hand, a flow which varies with time is called a transient flow. For transient flow, the streamline, streakline, and path line are all different lines. The governing laws of fluid motion can be derived using a control volume approach. This is equivalent to a fluidic black box, where all we know about the flow is what's going in and what's coming out of the control volume: mass, momentum, and energy. The control volume can be fixed or moved with the fluid. When analyzing a control volume problem, there are three laws that are always true: conservation of mass, conservation of momentum, conservation of energy. The conservation of mass gives us an easy way to determine the velocity of flow in a tube if the density is constant. If we can determine or set the velocity at some known area, the equation tells us the value of velocity for any other area. The quantity density times area times velocity has the dimensions of mass divided by time and is called the mass flow rate. This quantity is an important parameter in determining the thrust produced by a propulsion system. As the speed of the flow approaches the speed of sound, the density of the flow is no longer a constant, and we must then use a compressible form of the mass flow rate equation. Bernoulli's principle states that the total mechanical energy of the moving fluid, comprising the gravitational potential energy of elevation, the energy associated with the fluid pressure, and the kinetic energy of the fluid motion, remains constant. Imagine a fluid flowing through a pipe. As its speed increases, the pressure decreases, and vice versa. Let's see how Bernoulli's principle is applied in everyday situations. Take a straw in a drink. When you sip, you reduce the air pressure inside the straw, and the liquid rises due to higher atmospheric pressure outside. This principle is not limited to the straws. It's also crucial in the design of carburetors in cars, ensuring an optimal air-fuel mixture for combustion, or an airplane wing. Its shape is designed to create different air speeds above and below the wing. As the air speeds up over the top, the pressure decreases, creating lift. This principle is essential in the design and functionality of aircraft. Hydrodynamic calculations involve the detailed analysis of fluid behavior, a task that often exceeds the capabilities of simple mathematical solutions. Due to the nonlinear nature of fluid dynamics and the influence of factors like turbulence and varying geometries, these calculations become too complex. To tackle this complexity, numerical methods, such as computational fluid dynamics, are employed. Numerical simulations break down fluid systems into manageable elements, allowing for iterative computations to approximate real-world fluid behavior. Whether it's predicting water flow in a river or optimizing the design of an aircraft, these numerical calculations provide a practical and precise approach to understanding and predicting fluid dynamics. Now that we have explored the principles of hydrodynamics, let's see how these concepts are put into action in the real world. Hydrodynamics extends its influence into the realm of aerospace engineering, particularly in the design and analysis of aircraft. The principles of fluid dynamics apply to both liquids and gases, and aerodynamics is essentially a specialized form of hydrodynamics, focusing on airflows. Engineers use hydrodynamic simulations to optimize the shape of aircraft wings, control surfaces, and fuselages to achieve maximum lift, stability, and fuel efficiency. Key concepts in hydrodynamics, like continuity, conservation of mass, and Bernoulli's principle, are crucial for understanding the intricate aerodynamics behavior of aircraft. At the core of Bernoulli's principle is the idea that as the speed of fluid, such as air, increases, its pressure decreases. This principle plays a vital role in explaining lift, the force that allows aircraft to overcome gravity and move through the air gracefully. As an aircraft travels through the air, the carefully designed shape of its wing creates a difference in pressure between the upper and lower surfaces, generating lift. This phenomenon is akin to the principles governing hydrofoils in water, lifting vessels above the liquid surface. The application of hydrodynamics goes beyond the mere design of wings. It extends to optimizing their efficiency. A notable feature on model aircraft is the inclusion of small upturned extensions at the wingtips, known as winglets. The primary purpose of winglets is to reduce drag and enhance fuel efficiency. By mitigating the formation of turbulent vortices at the wingtips, winglets help to minimize induced drag. This improvement is rooted in hydrodynamic principles, as the winglet's shape optimizes the airflow around the wingtip, reducing energy-wasting vortices. In essence, winglets leverage hydrodynamics to enhance the overall efficiency of aircraft, contributing to fuel savings and environmental sustainability. One of the most prominent applications of hydrodynamics is in naval architecture and ship design. Engineers and naval architects employ hydrodynamic principles to optimize the shape and structure of ships, ensuring efficiency, stability, and safety. By analyzing fluid flow around the hull, they can minimize drag, enhance propulsion efficiency, and reduce fuel consumption. Hydrodynamic simulations and experiments help in designing vessels that can navigate through various sea conditions with optimal performance. Hydrodynamics play a critical role in the design and operation of submarines. Submersibles must navigate the underwater environment with minimal resistance and noise. Hydrodynamic principles guide the shaping of submarine hulls to achieve streamlined forms that reduce drag and enhance stealth. Understanding the complex interactions between water and the submarine surfaces is crucial for achieving optimal performance and maneuverability. The human circulatory system relies on fluid dynamics to ensure the efficient transport of blood throughout the body. One of the primary applications of hydrodynamics in medicine lies in the cardiovascular fluid dynamics. Understanding blood flow patterns and pressure variations within the circulatory system is essential for diagnosing and treating cardiovascular diseases. Fluid dynamic simulations enable clinicals to visualize and analyze blood flow, helping identify areas of turbulence, potential blockages, and the risk of aneurysms. Additionally, hydrodynamics plays a critical role in the design and improvement of cardiovascular devices, such as artificial heart valves and stents. Engineers utilize fluid dynamics principles to optimize the performance and longevity of these devices, ensuring they function seamlessly within the dynamic environment of the human cardiovascular system. Another significant application of hydrodynamics is the study of respiratory fluid dynamics. Inhalation therapy, commonly used for treating respiratory conditions like asthma, relies on understanding how aerolized medications move through the respiratory tract. Hydrodynamic principles guide the development of inhalation devices to ensure efficient drug delivery to specific areas of the lungs. Hydrodynamics also plays its role in the design and optimization of drug delivery systems. Intravenous drug delivery, for example, requires an understanding of fluid dynamics to ensure proper circulation and distribution of medications throughout the body. Microfluidic devices, which manipulate fluids on a small scale, leverage hydrodynamic principles for precise control over drug delivery, enabling targeted therapies with minimal side effects. Hydrodynamics isn't just confined to human-made systems. It plays a critical role in understanding and modeling the complex dynamics of Earth's climate system. In the context of climate science, hydrodynamics is particularly relevant to the movement of the ocean, the circulation of the atmosphere, and the interaction between these two components. The Earth's climate is a dynamic system where energy is exchanged between the atmosphere and the oceans, and the study of hydrodynamics is essential for unraveling the intricate mechanisms that govern this exchange. One of the primary drivers of climate is the ocean's role as a massive heat reservoir. The movement of ocean currents, a key aspect of hydrodynamics, redistributes heat around the globe, influencing regional climates and weather patterns. Warm ocean currents, like the Gulf Stream, transport heat from the tropics towards higher latitudes, moderating temperatures in regions like Western Europe. Conversely, cold currents, such as the California current, have a cooling effect on adjacent coastlines. Understanding the dynamics of these currents is crucial for predicting how changes in the Earth's climate, such as global warming, might impact ocean circulation and consequently regional climates. In addition to ocean dynamics, hydrodynamics is integral to understanding atmospheric circulation, another key component of climate science. The movement of air masses, driven by solar radiations and the Earth's rotation, creates atmospheric circulation patterns, such as the Hadley, Ferrel, and polar cells. These patterns influence weather systems and contribute to the distribution of heat around the planet. The study of atmospheric hydrodynamics helps scientists model and predict changes in weather patterns, storm tracks, and precipitation, all of which have significant implications for climate variability. Hydrodynamics also plays a critical role in the study of extreme weather events, such as hurricanes and typhoons. These powerful storms are fueled by warm ocean waters, and their intensification is closely tied to the transfer of heat from the ocean surface to the atmosphere. Understanding the intricate interplay between oceanic and atmospheric dynamics is essential for predicting the frequency and intensity of these events in a changing climate. Moreover, hydrodynamics is fundamental to the study of sea level rise, a consequence of global warming and the melting of polar ice caps. Changes in ocean temperature and circulation patterns directly impact the volume of seawater, and the intricate interplay of these factors is crucial for predicting how sea levels will respond to ongoing climate change. Accurate predictions of sea level rise are essential for assessing the vulnerability of coastal regions and implementing effective mitigation and adaptation strategies. In energetics, one prominent application of hydrodynamics is hydropower generation. Hydropower utilizes the kinetic energy of flowing water to generate electricity. The design of water turbines, which convert the energy of moving water into mechanical energy, relies heavily on hydrodynamics. The shape and orientation of turbine blades are carefully engineered to maximize the extraction of energy from the flowing water while minimizes losses due to turbulence and drag. Understanding the fluid dynamics and the vicinity of the turbine is essential for optimizing its performance and increasing the efficiency of energy conversion. In addition to traditional hydropower, ocean energy technologies, such as tidal and wave energy converters, leverage hydrodynamics to generate electricity from the natural movements of the ocean. Tidal energy systems harness the energy from the rise and fall of tides, while wave energy converters capture the energy from the oscillations of ocean waves. The design of these systems involves a deep understanding of hydrodynamic forces to ensure efficient energy extraction and device durability in the challenging marine environment. Hydrodynamics also plays a critical role in the development of wind energy. Wind turbines, which convert the kinetic energy of moving air into electrical power, are subject to the principles of fluid dynamics. The design of wind turbine blades, their shape, length, and orientation is carefully optimized to capture the maximum amount of energy from the wind. The study of atmospheric hydrodynamics is essential for predicting wind patterns and optimizing the placement of wind farms to maximize energy production. In the field of renewable energy, the development of underwater turbines for harnessing the energy of ocean currents is an emerging application of hydrodynamics. These turbines, similar in concept to the counterparts in rivers, aim to extract energy from the kinetic movement of water in ocean currents. The design of these underwater turbines must account for the complex and dynamic nature of ocean currents, requiring a deep understanding of hydrodynamics for efficient energy extraction. As we have seen, hydrodynamics isn't just a subject confined to textbooks. It has profound implications in our daily lives and various industries. In aviation, the principle we discussed are the reasons airplanes can soar through the skies efficiently and safely. Ship design relies on hydrodynamics to navigate the vast ocean with stability and speed. Medical applications demonstrate how understanding fluid dynamics can lead to advancements in healthcare and drug delivery. Hydrodynamics is a vast and evolving field with endless possibilities. Whether you are interested in engineering, biology, meteorology, or beyond, these principles are a gateway to understanding the world around. Thank you for your attention. Have a good one.